Well, welcome everybody. Nice to see a full house today. We're going to go through a lot of, detail on windows, kind of like feeding you with a fire hose, but we try to make it as simple as possible. So here's the agenda for today. So we've gone through the first couple. We're going to talk first about good window design. So if you're always wondering about low E or wondering about coatings on windows, double glaze versus triple glaze, this is the presentation that talks about the design part. Any designers in the room? No designers? Any energy modelers? One energy modeler? Okay, good. Well, I'm one, Mark's one, so. All right, excellent. Okay, so, and then the second part, we're gonna go through a little more of the technical side, dealing with thermal comfort, dealing with HVAC systems. Do you ever have problems with condensation on windows? People complain about frost on windows, right? Those kind of things. And then thirdly, we'll have a presentation on installation, which relates specifically to what CSA A440.4 installation relates to. So if you've never heard of that, we'll explain what that is. We'll explain what's coming up in the new codes, what's coming up with CSA, and then we'll finish off talking about how do we test things. If you have a leaky window, how do you test it? If you're building a multi or an apartment building and you want to make sure your details are really good, you know, you do a mock-up, you test it, make sure it's performing right. There's a way to do that too. So we've tried to cover everything in the entire spectrum of window design, window installation, comfort, everything related to that. So as we go through, the more questions you have, the more interesting it is for presenters. So we get to actually communicate and talk to people instead of us just talking. You know, if you've ever been on a seminar on Zoom and it's one person talking and everybody else is, you know, not really paying attention. Well, this is an opportunity to ask questions. There is no dumb questions. There's just dumb answers that I can provide. But, you know, we want to go through and learn lots of different things. So here's the outline. You know, we talked about it briefly, but if there's anything specific in here that you want to know about, you know, make a note for yourself to put your hand up or to ask the question. You don't even have to put your hand up. Just shout out a question if you have a question about a specific detail. Now, why are we talking about windows and energy efficiency? Well, if you think about windows as a whole, what's the biggest problem in the wintertime with windows? You get condensation. You get frost. People complain about how cold they are. And then the problem in the summertime is they're too hot, right? So we have these units that we put in there to let light in to see the world, and, you know, they create all sorts of problems. And then on the energy side, we go to model a house and we go, the code says I need a U value of 1.6. What the heck is that? And then the windows show up and they've got a U value of 0.28. What does that mean? Well, you know, if there's imperial, there's metric U values, what's the difference? Then there's the solar heat gain, which implies, you know, how much heat's coming through, how big of an impact does that have? So overall, there's all these things that we have to learn about windows. So when you look at the first note here, it talks about the fact that, you know, our government decided way back that we wanted to have energy efficient housing. We wanted to move towards net zero ready housing. But part of that is the window itself, because if you're modeling a wall, what's an average wall? What's the energy efficiency of an average wall? R16. So, not a bad number. What's the average energy efficiency of a window in that R16 wall? Yeah, very little, right? So, what would make the better impact? Would it be putting more insulation on the wall? Or would it be getting that window up as close to that R16 as possible? If you had an R16 window, you wouldn't be adding any extra insulation to your walls. Your building would perform really well. But you know what's interesting is, you ever modeled a house and taken all the windows out of it? Do you know what actually performs better if you add windows into a house and the windows are facing south and they have just a tiny little bit of solar heat gain? But then if you put too much solar heat gain in and they're all facing south, guess what happens? In the summertime, the homeowner's phoning you, like, what the heck kind of windows did you put in my house? I'm cooking. I can cook eggs on the dining room table. So that's the kind of thing we're looking at here. So here's the aspiration, 0.82 watts per meter squared per Kelvin. So what does that mean? Well, we're going to learn about that, but basically that's your U value in metric. So what are you using for windows now? If you're using a 1.6, look at the value we're trying to shoot for. It's quite a bit lower. So that's going to get us where we need to be so that we can achieve the net zero wall. So these are some things that we're going to talk about today and learn about today. There we go. So some of the basic mechanics of a window. We need to learn about, how heat moves and how heat loss works. So some of the basic mechanics. If we look at a window itself, how does heat transfer through a window? And why do we talk about heat transferring through and not cold going through? Well, the principle of physics is hot moves to cold. So when I talk about conduction, convection, and thermal radiation, for instance, if I stand near one of these windows, if it's minus 30 outside and I stand near one of these windows, and it's made of aluminum, it's got an aluminum frame, is it going to be warm or cold on a minus 30 day? It's going to be cold. And when I stand near that window, what happens to the heat that my body's producing? The colder the surface, the faster it sucks the heat off my body and it feels really cold. So that's what we call, which one? Conduction, convection, or thermal radiation?
The body heat one?
Yeah, the body heat.
Radiation.
It's radiation, right? Because it's sucking the heat off me. But if that's a hot surface, if that's a fireplace, am I standing beside it? Which way is the heat transfer? It's from the fireplace to my body and it feels warm. So the reason we feel cold in a house in a lot of cases is because that surface is the coldest surface of the house. So thermal radiation. When we transfer that thermal radiation through, we can do things to a window to adjust how much goes through, which is what we call solar heat gain. Can we reflect the heat that's in this room back into the room by putting a coating on the glass? And in the summertime, can we reflect the heat from the sun outside by pushing that back out to the exterior and not letting it into the building? And how do we find the sweet spot between those two? When we talk about convection or the movement of air, do you ever have a customer and they go, come here, let me show you this window. They take you up to the bonus room and they've got this massive giant window and they go up there and they take their lighter on a cold day and they go like this and the flame goes like this and then goes out. And they go, see, there's a hole in the window. Is there a hole in the window or what's happening? It's convection, right? Warm air rises, cold air falls. If you've been in Alberta long enough and you've been in a Chinook, you know what happens when warm air meets cold air, right? Creates a wind. So we get convection, which moves hot to cold. So how do we reduce convection on a window? And then the first one, conduction. Well, what's better, an aluminum window or a wood window? Wood. What's better, a wood window or a PVC window? Depends on the type of wood. Softwood's better, hardwood's less. So it really comes down to the type of material. And then we put a thermal break in that window. So we have a piece of aluminum here, we put a piece of rubber between it and a piece of aluminum here, and we get a thermally broken window. It's warmer than a straight aluminum window, but it's broken. So we need to think of those parts of the window. Now, there's other parts when we get really in finite detail. So with a window, where's the weakest part of the whole window? It's going to be in the frame. It's going to be the transfer of heat through the frame. So things that you want to remember from this slide are going to be, if we look at the coatings, the glass surfaces, that's an important one. If we look at the gas that's going to be in between the layers, and then the spacers, and then the type of materials on the window. So those are the details that we need to look at. So when we talk about a layer on the window, we start from the outside. So that's coating one. And then from there, we move inwards. So anything on the left in these slides is outside, and it starts with coating one. So you got coating one on the left, the middle's coating two, the middle of the backside is coating three, and the inside coating's four. So we're going to give you a whole bunch of different window examples as we go through. The gas fill, what kind of gas can you put in between the layers of glass. What can you put in between there? Something that Superman's afraid of. Kryptonite. Krypton, right? So krypton gas, super expensive, but typically you're going to just have regular air or argon. So what does argon do? Argon's a heavier gas. It's more dense. So it slows the transfer of heat through the air. So that's all it does. The heavier the gas, the slower the transfer of heat. So that's going to help us as well. Now, when we get into coatings, low emissivity coatings, or low E, that's going to bounce the light back. But more importantly, it's going to bounce the heat energy, the infrared rays back. So that can work from the inside out, that can work from the outside in. And there's different types of low E coatings as we're going to discover here. So as we go through, if there's any questions on these, just fire them out. But here's the basic things that we need with a window. We have a U factor, and we always want to look at a metric U factor. Understand the U factors. If we're into the 1.0, 1.2, 1.6, that's a metric U value. If you get something from your supplier that says 0.4, 0.28, that's an imperial U factor. How do you convert imperial to metric? Calculator, Google. 5.678 is your calculation, right? So U value. What's more important, U factor or solar heat gain coefficient?
Trick question.
Trick question. It is really a trick question. So solar heat gain coefficient, how much heat comes through the glass? Right, so if I have a solar heat gain coefficient of a 0.7, is that a good window or a bad window? Depends on where you are. If I have a 0.7 on that window and it's facing south and it's a sunny day and it's summertime, are we going to be able to stand being in this room? It's going to be pretty hot, right? But if that's a 0.2 window, then it's pretty comfortable. But what about reverse that in the wintertime? 0.2, I'm not getting any free heat from the sun. So my energy bill goes up. So understanding that is important. So we learned very early when the new energy code came in back in 2016 that I could really cheat that code by putting in a 0.7 window. Right? I would overheat the house like crazy, but I sure made it easy to achieve, compliance with the energy code. So now we have things called peak cooling loads, which really are influenced by the solar heat gain. And you guys can jump in if you're energy modelers, just jump in. If I get something wrong, it's been a long time since I've done a lot of this, but. So then the third one is visible transmittance. Visible transmittance. That's how much natural light is coming through the glass. Is that important? Sure it is. The more coatings you put on, the lower the visible transmission becomes. Because sometimes when you get really, lots of coatings, you can really reduce the amount of visible light coming in. And sometimes it's noticeable, sometimes it's not. So, yeah, absolutely.
I just wanted to jump in because I think this slide is really important. It's really weird to talk to a mic that's not on speakers, but I know it's for the video. Anyways, I'll do my best. It's really important because these terms, we're going to say them over and over and over again today. So just to highlight, I like to think of solar heat gain coefficient very simply because it's actually a very straightforward metric. The 0.7, 0.2 is on a scale from 0 to 1. So you can think of it as the percentage of sunlight energy that's allowed to come in, right? 0.7 is 70%. And if it's 0.2, it's 20%. U factor is not on a scale like that, but U is the opposite of what we're much more familiar with, which is R value. R value is the resistance to heat flow, so higher numbers are better. U value is the ability to transfer heat, so lower numbers are better from a thermal insulation point of view. And those two terms are going to come up for the next 3.5 hours, almost every 10 seconds. So I just wanted to pause and highlight that on this slide.
Excellent. Thanks, Mark, because that is really important. And how do you get the U value? Because it's the reciprocal of the R value or the RSI value. It's really, if you know the U value and you go 1 divided by U value, you get the RSI value. If you know the RSI, 1 divided by the RSI gives you the U value, right? It's the reciprocal, it's the opposite. Okay, and again, any questions, just throw them out. Okay, so in terms of window heat transfer, maybe when you bought windows, maybe on the window schedule, you've noticed it's got an ER rating, right? So it's an energy rating. It's used by CSA to determine in cold climate how effective your windows are at several things. So for instance, if you look down here at the bottom, the ER rating is basically solar heat gain times the constant, which isn't shown in here, minus the U factor times a constant, minus air leakage at 75 pascals, plus a constant. You're good with this? Anyway, so what it really is, it's a formula to calculate, and there's no test on this at the end, so no worries. It's a formula to calculate how that window is going to perform. So I know when we started doing energy modeling in 2016 to the new code, window manufacturers would send us out literature, and we're trying to do performance modeling, and they'd send us out the window schedule, and they say, well, these windows are a 25 ER. I can't put that into the energy model. I need to know the solar heat gain, I need to know the air leakage, and I need to know the U value. But that's what that is. It's a way to calculate those three metrics to figure out what efficiency or efficacy that window is. So that's one that you might hear come up. So the higher the ER value, see at the bottom here, the higher the energy performance of the window. So if you're dealing with things like Energy Star or any of the, the higher end energy modeling certifications that you, not modeling, but the, what do you call it, Energy Star. Anyway, it's compliance pass. So if you're dealing with any of those, then that's what you're going to look for is the ER.
And I just want to jump in. That last few words in that sentence are important. The higher energy performance in the heating season. And one of the things that the code has started to recognize is that selecting windows on the ER rating alone doesn't tell the whole story. And it kind of turns a bit of a blind eye to the impacts of that solar heat gain number in the formula and what that does in the cooling season. And as we experience warmer and warmer summers, that's coming up more and more.
Yeah, and I think that's important to understand, especially when you're into the warmer parts of the country. So we don't see a lot of that in Edmonton, Red Deer, Calgary, but you get into the southern parts of the province, you get into BC, you get into Ontario, and Eastern Canada. Those are becoming very, very important. You've heard of the term peak cooling load, right? Which is a big controversy right now because we're overheating houses. People are dying because there's too much heat coming through. So we're trying to come up with a formula to deal with that. But this ER rating is just heating season, like Mark said. All right, so another part of the component, and probably the weakest part of the component, is the window frame. If I have a giant piece of glass like this or like this, what do you think the R value in the middle of that glass is? High or low? Or do you think it's the same? It actually can be pretty high. Like you get a giant chunk of glass there in a triple glaze, the middle of that window could be R12. It could be super high. But as you get closer to the frame, it gets colder and colder and colder. So the frame becomes one of the most important parts because we take an average. When we take a window, we take the center of the glass, we take the edge of glass, and we take the frame, and we combine those numbers together to give us the overall value of the window. So when we're looking at a frame, we need to figure out, is that frame going to transfer heat through? And where the frame holds the glass and where the glass is supported onto that frame, how do we stop the transfer of heat through at that point? So there's different types of frames that we could look at, but some of the things that we need to consider first is the IGU, or the insulated glass unit. So we have the glass unit and we have the frame. So the glass unit is affected by a number of layers of glass. So we know that a triple glazed window is going to perform better than a double. It's going to be much more comfortable than a double. We know that low emissivity coatings can have a huge impact on the amount of heat that comes through. So whether that's a good thing or a bad thing, depending on your climate zone, depending on where the window's positioned. The gas fill, or what's the density of the material between the glass? Because that dictates the transfer of the heat. And then the last one, the spacer system. So the spacer at the bottom. In the old days, you had a piece of stainless steel that would fit between the windows, maybe a piece of aluminum if you go back far enough. right? Now they have the piece of stainless steel and they wrap that with rubber, and then they put little spacers in there, maybe a little bit of desiccant in there to try and absorb moisture. So there's all sorts of things that they do with these windows. So if we look at the two units together, that gives us the overall R value or the overall U value of the window. Now, some of the things to consider about the glass layers. We talked about the fact that down here, we're moving towards a 0.82 as a standard window. So we're getting closer and closer there, right? The new codes are getting us closer and closer by the time we hit 2030. I don't know if we'll make that, but that's the goal. But we have different options to get there. So a double glazed window, there's some pretty high performing double glazed windows nowadays because of all of these different things you can do to them. But again, a triple glazed window is going to give you the most efficient way to achieve that. But then you also have quad windows. And I don't know if anybody's seen these filament windows where they have multiple layers of really thin glass. You know the glass that you put on your phone cover, right? So they have like 5 or 6 layers of that in between. And they're achieving these ridiculously high values. But what's the cost and how long does it last, right? It's super sensitive to movement and everything else that goes in there. So you have all of these different things that you can use, but we're going to focus on the double and the triple glazed windows. So background, a little bit on low emissivity glass, right? When we started using low emissivity back in the 60s and 70s, and then we moved forward, we started with coatings that were put into the glass when it was liquid, when it was molten. I think we call that pyrolytic glass. And it had a little bit of effect, but it's not until we get into the 2000s that we start to see really good low E or protective coatings on the glass to reflect that light energy or that infrared energy. So when I look at something like this, I thought, when I first saw this presentation, I thought, this is really interesting because, you know, I remember people talking about the hard coat and the soft coat. And I think HOT 2000 has to catch up on all of these new terms because it's still in a bit of a dark ages. But when we look at these different coatings, the two most common is the pyrolytic and the vacuum sputtered. Now, you probably won't see a lot of pyrolytic because that technology is kind of gone away. So a lot of our glass will have a vacuum sputtered. The benefit of vacuum sputtered is we can get into very low solar gain systems. So pyrolytic, high solar gain only. So you're only going to achieve a certain amount of reflection. You're never going to get that really low value. But with vacuum sputtered, depending on how many times you pass that through, you can get single coat, double coat, or triple coat. So that is what dictates how much heat goes through that glass in terms of solar heat gain. So when you get into a triple coat of silver coating, 3 layers, you get a very low solar heat gain. So you're seeing windows down at 0.2, 0.25 solar heat gain. So you're almost getting no heat from the sun coming through them because of that. So what do you think that impacts on a window? If you put more coatings on, what's the end result?
Visibility.
Yeah, so it starts to get darker, darker, darker. So you get lower visibility. So we're going to touch on that here in a bit. But if we just look at several windows here. So these are double glazed IGU, insulated glass units. So remember, the coatings or the faces on the coating, or the coating on the faces is from the outside to the inside. So this would be face 1, 2, 3, 4. So on a double glaze, we only have 4 options to put coatings on. So we could put the coatings on 2, 3, 2, 3 together, 2, 4 together. What would be the problem? Why is this crossed out, do you think? This third one here. If you put, it's trapping. What's it trapping? Exactly. So because it's bouncing back and forth, that's going to create a lot of thermal stress in that window and that glass. So you want the heat to be reflected either back into the building, or be reflected out. In this case, it's reflected back in. Whereas this one here, it's going to be reflected against each other, and then you're going to get a lot of thermal stress. So we rarely put double, coatings on the inside to bounce back and forth to each other. So that's an interesting thing, I thought. When we get into these specialty coatings, one of the other things with the coatings on the inside is it has to be durable enough that it doesn't come off. Imagine your painter comes in, he gets some overspray on the glass, so he takes a razor and just, right? So it has to be durable enough. So we don't often see coatings on the inside in 4. So we went through that phase where we did. Now with modern windows, we're not seeing it as much. We'll go to a triple glaze window. Here's where we start to get into, a significant amount of options. If we go back to this one, we had 4 options where we could put the coatings. We put a triple glaze in. We've got 3 pieces of glass. Now the options get huge. So you look at the options here. Again, you can put it on phase 2. You can put it on phase 5, 2 and 4. But notice where it's located and the difference between, say, this one and this one here, or this one here. How is it that this one can reflect the heat back in? Remember in this one, we said we don't want to have the heat bouncing in and out. Whereas this one, the reflection in between, it's not bouncing it towards this surface here. It's going to bounce it in here, and the heat buildup stays in this cavity. The heat buildup here stays in this cavity. So we just don't have that bouncing back and forth when it's a single cavity. We can have the coatings on 2 sides of the cavity facing inwards as long as there's a separator in between them. Because remember, these are sealed units. Insulated glass units are sealed units. So those are some of the options in terms of triple glazing. So we look at the coating use and we look at the type of coating it is. So remember we said that there's a single coating, which is low emissivity, or which is high emissivity. There's a double coating medium, and there's 3 coatings, which gives you low emissivity. We can combine those now, right? So surface 2, you could have high, medium, or low right here. And depending on which one you have, that dictates what the solar heat gain of the overall window is. If you go surface 5, you can only do high solar heat gain coatings. So the reason for that is we don't want to create thermal stress. So the window manufacturers look at this and go, how do we prevent from overheating our windows, especially south-facing windows? So we have these different coatings on these different locations because we don't want to have problems with the windows themselves. And a lot of this we've learned from experience. So we're getting into that sweet spot in design and manufacturing of windows where we've learned all this stuff, we've made all the mistakes, we've put them in the field and had them fail. And now we're getting into some fairly good designs and good ways of building windows. So we've got the insulated glass unit, we've got the frame. Now we get into what's the U value, what's the solar heat gain, what's the visible transmission. And what do those different coatings do on that? So up at the top here, we've got a U value of 1.48. So this is a high solar heat gain window. So the solar heat gain is 0.68. So on a sunny side of a house, that's going to create a fair bit of heat. So what dictates the amount of heat that's going to come into the building? Like if the window's this big versus the window's, massive, that's going to be the amount of heat that's coming in. So that's the other factor to look at, is the size or the area that's coming in. Now, if I look at these 2 windows, 1.48 to 1.42, not a lot of difference in the U value. In fact, if I go across here, 1.37, these windows are all very similar in U value. But look at the difference in solar heat gain. And what's the difference in the coatings? It's really the location of the coating and whether it's a high single coat or whether it's a low triple coat coating. But look at what happens to the visible transmission as we go down this path. Now, if I want to increase or decrease my U value and I want to make a better window down to 1.11, these two windows are almost identical except for the U value. But what's changed? I've added an interior low E coating, and remember, we're radiating the infrared spectrum, so by putting that on the interior, all the heat in the room gets bounced back into the room. So I haven't really done anything to the window itself other than put a coating that bounces the heat back into the room. And by doing that, I've taken that from 1.37 to 1.11 in terms of a low E coating. Does that make sense to everybody? So we can use these coatings to our advantage. So should I order windows for my house and put the coatings on the exact same spot on all four sides? Not necessarily, because we can really fine-tune that house so that the windows on the south and the west into the sun perform differently than the windows on the north and the east. And so we can really fine-tune it and get really huge benefits. Go ahead, Mark.
I just wanted to ask a question, because we asked at the beginning, so got a lot of answers. There's a lot of builders in the room, but I wanted to drill down into that a little bit and ask how many of you are custom home builders? So maybe show of hands if you build custom homes, handful a year, a few of them. How many are more tract builders, developer, build subdivisions? How many of you are in the room? A few of those as well. I would suggest that customization by orientation is a different problem for those two different categories of home builders. Wouldn't you agree? Like if you're trying to track different windows on different sides on a model that is being built in different orientations in a subdivision, that's pretty complex. Feels to me like the chances of maybe putting the wrong window on the wrong side are pretty high. In a custom home scenario, you've got a lot more ability to control that. You're getting one set of windows and you have that chance for optimization. So I think maybe keep that in mind as we think about consistency and simplicity for your process versus the ability to fine tune windows with this. The other thing that I just wanted to flag on these slides, how many of you are getting concerned as you see the visible transmittance drop from 0.79 to 0.63? You start to get nervous that people are going to complain about a 0.63 window?
Can't grow plants.
Can't grow plants in a 0.63 window? Is this from experience?
No, not in my house, but.
Okay. It's an interesting point. I've never heard that one before. I'd be curious to know if that actually takes effect. But my experience has been that if you don't see those windows side by side, you could never tell. If you ask most people to look at a window and give a guess of the visible transmittance as a 0.6 or a 0.7 or a 0.8, they wouldn't know unless they see two of them side by side. So if the whole house has a 0.65, every window in every orientation, it doesn't stand out that it's lower than a 0.79 because you don't have a comparable. So don't get too nervous about those numbers going down until you get really low and it starts to get into tinted glass. That really starts to affect things.
Yep,
Thanks
exactly.
for letting me jump in.
No, yeah, jump in anytime. So, and anybody else, if you have comments on anything that you're seeing from experience especially, then we'd love to hear that too. But these are important things to think about. So if you look at, for instance, center of glass U factor. So this is ruling out the frame. This is just talking about center of glass. So when you look at these different products and you look at the solar heat gain, you know, a 1.42 to a 1.48 is not huge, but again, the solar heat gain is huge. So, and the only difference between the two is the positioning of that layer and whether it's a double coat, triple coat, or a single coat. So that's the big difference in here. So it doesn't take a lot to get to these. So when we're talking about center of glass, the other thing that this one has is argon filled and 3mm glass. So the thickness of the glass itself makes a difference. The spacing on the glass, the type of gas between the glass, those are all important factors. So this is probably way more detail than you need, but it helps to appreciate what kind of things to consider when we're looking at windows. This one I thought was really interesting because a lot of times we get a triple glazed window and we think, well, that should be, way better than a double glazed window. But not necessarily, depending on the coatings and the position of the coatings, the thickness, and then the glass materials. So when you look at the center of glass for this material, triple glazed, center of glass, argon, 3mm glass, 1.03 is probably an average triple glazed window. That's probably typically what you would see. So it's got a solar heat gain of 0.25. The biggest difference between double and triple is solar heat gain. You can't get enough coatings on a double to reduce it significantly. So you look at some of these numbers here, 0.25 without just a single layer. Or here you're getting at 0.25 and you've got two layers. You've got a high and a low E. But look at what it does to the U value. All you changed here was adding that center layer on number 4 of high solar heat gain, and you basically got a window that's going to perform 25 to 30% better. So using the coatings, using the argon, using the double versus triple really helps you impact where you want to put those windows. And especially like Mark said, when you're doing a custom-built house, you can really position those, especially those custom-built houses that, they want that massive amount of glass on the backside so they can see the view. Well, you can take advantage of these, especially when you're south-facing. When I look at this one here, and you look at the difference here from a 7.5, 0.74, 0.72, almost identical. And yet, look at the difference here, 0.56 to 0.25. So again, if I'm doing a custom home and I'm looking at the overall heat gain and I'm looking at the percentage of glass within there, I want to know how much heat's going to be generated by that glass and, where to position that. Because I want that homeowner to feel comfortable. I don't want them to overheat, but in the wintertime, I want them to be warm enough. So again, looking at this and understanding the basics behind coatings, where they go, talking to the sales rep from the window company and saying, here's what I want in this wall, here's what I want in this wall. And if you're a custom builder, or a track builder, what are we finding for an average sweet spot for those houses? Where are those windows? What's position the house is facing? So any questions on the coatings, low E coatings, or positioning of low E coatings? Anything that jumps out at you? All right. The argon versus krypton. It used to be, I know when I was site supervising, krypton gas just started to come out. And, you had the option. You could order krypton, you could order argon. They were just about the same price. The problem is that krypton gas has become very popular for the aerospace industry. And so the price of the product has gone through the roof. So the cost of krypton, $30,000 to $50,000 for a tank versus $30 to $50 for a tank of argon. So you're probably not going to see a lot of krypton gases used in windows. So when we look at the spacer system, or the little block that's between holding the glass apart, this can have an impact in the overall frame connection as well. How much heat is being transferred through this joint? So like we said, there's an aluminum one, there's a stainless steel one. Anybody know what the difference is in thermal conductivity between aluminum and stainless steel? A huge amount, right? I think it's something like 220 watts per meter squared for aluminum, and it's like 15 for stainless steel. So that's why you'll see a lot of stainless steel fasteners holding on exterior insulation versus using a regular nail, because it doesn't transfer heat as quickly. So we get all these different types of spacers. So we can have aluminum spacer, which will have a rubber coating around the outside, which is part of that thermal break. You can have just a stainless steel spacer. It might have a foam or a rubber internally. And then you have the foam spacer systems. Now the difference is, how do they perform long term? So you can imagine on a sunny day in minus 30 weather, it's minus 30 overnight, the sun comes up, it's beating on the backside of the south of the window. That window frame is going to go from minus 30 to plus 30, 60-degree swing in about 4 hours. And then the sun sets and it goes the opposite. So you get these extremes in temperature. So depending on where you're building, you might want to pick something like this that's going to give you very good long-term performance. So it's not just about the thermal transfer, it's also about the performance of that unit and that material. So those are things to consider when it comes to the IGU or the spacer. If you're spending a lot of money on a window and the coatings and the gas, then something that's going to perform really good is probably worth the money. The width of the spacer, right? The amount of space between the two pieces of glass makes a huge difference. So it's got to do with the convection occurring between the glass. So moving those in and out will impact that. But there's another thing that it impacts, and that's sound. So sound attenuation, when you put windows in, if you build in, say, for instance, Edmonton or Calgary, and you're near the airport, you have to adjust the width of the glass in those locations because there's certain vibrations, and by adjusting the glass, you can get rid of those. So there's optimum spacing. So when they're doing modeling on windows, you know, they're looking at the spacing, the type of glass, you know, they're getting the sweet spot. You know, because if you space it this much and you put this spacer in and you put this coating on and then you put this fill in, this gas fill, you can achieve that 0.82 for a triple glazed window. The type of window frame makes a huge difference. So here's an example of 4 window frames. Now again, these are U values. So if you take an average aluminum window that was built before we started doing thermally broken windows, you go from about a 7.8, and you thermally break that window so that the outside frame is not in contact with the inside frame. There's a rubber connector between the two. Look at what happens to the U value. Drops almost in half. Now, if you take that, instead of doing an aluminum window and you make that a PVC window, you drop that to 1.8. And the reason for that is because the thermal conductivity, the transfer of temperature or heat through that PVC is really low and slow. And then if you could, and you just took a piece of foam and you molded it, and you use that for your window frame, there's the value that you would achieve, 0.76. You wouldn't have any structure to it. It wouldn't perform long term, but you could get a really good insulated window frame. So now if you're into that window frame at 0.76, and that's the center of glass, that's a pretty high performance window. So you can see what happens here. We have to get our window center of glass really, really high to offset if we're putting a window in like this, where it's a 1.8, because it's the overall average that our window is designed to. So when we look at heat transfer through different materials, for instance, here we have a softwood material. It's a pretty good insulator, 1.66. Hardwood, 1.91, just a little bit higher. PVC, 1.73, so, you know, somewhere between these two, and then aluminum, not so good. So if you're using aluminum windows, if you're using these type of windows, storefronts and custom homes, you need to tell your homeowner, expect to have condensation, expect to feel cold, unless you offset that with a ton of heat that's showering that window. So those are the things to think about, especially with custom home building, depending on the type of materials that you're using. Any questions on those? Go ahead.
We're talking about different materials. Is there any comparison with the fiberglass windows also?
Fiberglass is really low. Do you know off the top of your head what?
I don't know numbers off the top of my head, but yes, they generally perform very well. And they have the added benefit that the frame and the glass expand and contract at roughly the same rate because the frame is glass material as well. So they are considered these days to be a very good choice for high performance windows.
Yeah, yeah. One of the top selections or top benefits, top products. So the next thing we look at is when you look at a window, you take a cross section, what do you notice? It's all compartmentalized. It's all little different cavities. So if I look at this window here, where I have an open cavity, there's no, there's nothing compartmentalizing that cavity. What does fiberglass in the wall do? It compartmentalizes everything so that this little bit of air here doesn't touch this little bit of air here, right? It keeps the air in little pockets. So it's the same thing with windows. So if this is a 2.57, and I throw a few little compartments in here and drop it to 1.8, look what happens when I put more compartments in. Now I'm at 1.74. So that's another way that we reduce the overall energy loss of a building or reduce the thermal bridging of the windows is we use windows that have these tiny little compartments. And then if we want to take it one step further, we fill those compartments with foam. So you're starting to see that now where they'll offer that option where they have the compartmentalized window and then they fill those cavities with a little bit of foam, probably urethane foam, and then you're down at 1.22. So now you're getting into that low value because remember, it's center glass, edge of glass, and frame that gives you the overall average for that window. The other thing that's interesting is, you know, when you go through the first winter, what's the complaint that your homeowners often have? It's condensation on windows. In fact, it's probably not even condensation. It's probably more frost on windows, right? What's the difference between condensation and frost? One's a solid, one's a liquid, right? Really, it's the temperature of the surface. If you've got condensation on the window, that surface of the window is above freezing. If you got frost on the window, that surface of the window is below freezing, right? And the vapor in the air either goes straight to a liquid or straight to a solid. But it can convert backwards the same way. So when we're looking at condensation resistance, there is a condensation resistance number. And the higher the number, the more resistant it is. Do you think a better U-value window would get you better condensation resistance? Higher performing window, better condensation resistance. True or false? True. It would seems reasonable, right? However, look at these numbers here. So which window of these four gives you the best condensation resistance? 1, 2, 3, or 4? Number 3. There's your condensation resistance. Higher number is better. 77. What's the total U value of this window? 1.02. Look at this window. There's a 0.82 window. But look at the condensation resistance. It's worse. So do you ever rate your... Sorry, go ahead.
Because of that inside coating?
Well, yeah, look at the coatings. The location of the coatings makes a big difference. So look at this number and look at where the coatings are. So now you start to see a correlation between the location of the coatings, the reflection of heat, and the resistance to condensation. So this one is reflecting all the heat from outside back in. From here, it's reflecting the heat that's trying to come out back this way. What does this coating on number 6 do?
Keep the heat in the room.
Yeah. So it's reflecting heat back in. So it's reducing the ability to keep this warm because a high emissivity versus a low emissivity. One's going to absorb more energy and one's going to reflect more energy. So if I look at this one, there's no coating here. So the heat from the house is going to absorb into this piece of glass. Whereas this one, it's going to reflect the heat from the house. So this one is going to perform better from an energy efficient standpoint because the heat that's in the room is trapped in the room. It bounces off the glass back in. But this one is going to perform better because the heat from the room warms this piece of glass up. So it seems counterintuitive. Chelsea.
When you're selecting windows, this information's not apparent, so how do you make the right choice?
You have to ask the window manufacturer. So they do have these, but one thing you could ask, like when you're designing a house and you're looking at windows, you could ask, I want a window, like typically how do you start with a window manufacturer? You know, you phone them up and say, I need some windows for my house. What's the cheapest you have? Right? That's one way to do it. Or you might say, I need some windows for my house. I want something in the 1.1 U value range. So what other criteria have we learned about this morning other than just asking for a 1.1? What's the second most important?
Position of the coatings.
Position of the coatings, which dictates what? Solar heat gain. So do I want a lot of free heat in the summertime? No. I want to bounce it out in the summertime. Do I want free heat in the wintertime? Absolutely. So now I'm looking at that, and then I'm going, what's the risk of having condensation in this house? And that's dictated by the coatings, not just, you know, the overall U value, but the coating. So how do I offset that? Let's bring in the other parts of the building. So there's my window right there. I have a homeowner that likes reasonably high humidity. I've established that during the sales process. They like high humidity. I don't want to have condensation on my window. So you probably want this window, but then you look at this and you go, well, that's not going to perform very good on a net zero house, so I want this window. How do I offset this on that glass? Air movement. All I need is a big fan there pushing air at the window, and my condensation issue goes away. If I don't want to move air, then I worry about the condensation resistance. So I don't have to just use the windows. I can use the mechanical system, air movement. You know, if somebody wants insulated blinds, then I want that window. If they're not worried about insulated blinds and they allow air to move through, or maybe I put ductwork right in behind the insulated blinds to push warm air up there, or I put a fan there to push warm air up there, then I can go with that window. Mark, you look like you're...
Well, I have a question. I'm going to put you on the spot, Darrell, because if you asked me, I would also be on the spot. What number's high enough for condensation resistance? And what scale is this on? And we actually got asked this question. I'm not going to make you answer that on the spot, but we got asked that question the first time we ran this workshop, and the best experts in the room were like, well, higher. Higher is good enough. You want to go as high as you possibly can. But I asked the question because if I saw a 64 condensation resistance, my first question would be like, is that good or is that bad? Am I in a bad window scenario? What is the risk to my homeowner here? Because that's really, at the end of the day, what we're concerned about, right? Is the homeowner going to hear from me that I'm putting in a super high performance window, and then the first sign of cold, there's condensation on the inside of the glass? What questions are they going to ask me for that? So it's a scale here. I think we have a handout that you'll be able to pick up down at the build booth after the show that has some answers to those questions. From memory, I think anything 65 and higher-ish in condensation resistance should make you sleep very well at night. But I just wanted to highlight that to say that we see differences in numbers all the time. But it comes back to what questions you're going to ask your manufacturer, your supplier. I really like that. And understanding how to ask about U value, understanding how to ask about solar heat gain coefficient, and then understanding that condensation resistance matters to your home buyers are three great talking points for asking questions that don't necessarily mean you have to remember which surface coating I'm trying to remember to get a triple on and a single. Leave that to the manufacturers to understand. It's important to understand how it all works. I think that helps us ask better questions. But at the end of the day, we're trying to figure out which questions we can ask our suppliers that address the concerns of our home buyers and our homeowners.
Yep. No, that's a really good way to sum that up. Question?
Is there an impact on the location of the window in the assembly of the wall? Does it affect those factors?
Absolutely. So question is impact on where the window is. So if the glazing, let's say you're doing an ICF house, and you move the glazing all the way to the outside, and somebody puts drapes on there, insulated drapes. How much heat's going to reach that window? Because this is really dictating, you know, the reason this one performs well is because it can absorb heat, but what if there's no heat there in the first place? So those factors do come into play, but don't rely on your window to be able to do that. If you take those two windows, these two windows, and you move them inboard so that they're flush with the interior face of the drywall, you've reduced the condensation potential on that window. So that's a really good question. When your homeowner has frost or condensation on the window, what's the simplest way to eliminate it? Air movement. What's the middle of the house? 35 degrees or 30, it could be 35 degrees. 35% at 21 degrees. Does that air have potential to absorb moisture? Absolutely. How do you get it at the glass over there? You open the curtains, you get the air movement, you turn the ventilation fan on, you get circulation going. So if that glass is sitting way outboard, right, when you put that building together, you might want to consider moving it inwards a little bit so that you're getting more air movement towards that glass surface. So this is just one of your toolbox, right? You've got ventilation, you've got air movement, you've got condensation resistance, you've got U value, solar heat gain, right? You need to put those all together. We talk about a building as a system. Here's a classic example of the windows being so critical in this system. Excellent. All right. We all know kind of what the window styles are, sizes. You know, I'm not going to spend a lot of time on this, horizontal sliding, casement, fixed windows. But when we get into window labels, and we look at window labels, these are important things that we should understand. So what would you look at? Like if you have a label, let's say we have this label right here, and I walk into the house, and I look at the label, what are the things listed here? So here it says U factor. So what would you say about this window, 1.44? Think that's a double or a triple glazed window? Probably a double. So it's a reasonably good double though, right? Because an average double is probably a 1.7, 1.6. How about 0.47 for solar heat gain? Is that too high, too low? It's a little bit high, but depending on the size of the window, like if it's in a bedroom and it's a 24 by 24 window on the side of the wall, it's south facing, it's going to let a lot of heat through, but it's probably not going to cook you in the summertime. If it's a giant mass of windows, then that's totally different. How about this number right here? It says energy rating, 35. Is that a good window or a bad window? That's a really good window. And then 0.42, visible transmittance. It's a little bit low, but like Mark said, you're probably not going to notice it unless the window beside it has a 1. Right? Because then you're going to visually see it instantly. Go ahead, Mark.
These labels are, I love this slide, because this is a really great example of understanding which number you're using to make your decisions. Because this is a very excellent energy rating score and a very good window if your heating season performance is your primary concern, right? But if you're worried about your homeowner's cooking because you're choosing big windows and you're in a warm location, I'd be more worried about this number than I would be about this number. So they don't all tell the same story. They're each giving you a different perspective on the performance of that window. Energy rating is very useful to get you in the ballpark because it's what they tried to do with energy rating is to come up with one number that gives you a sense of the quality of this window from an energy performance perspective. It's very useful. It's used in Quebec extensively to select windows and supply windows. But I think the takeaway that I would really like you to have from this session is it's not the whole story, and you have to look at the other numbers on the label as well.
Yep, exactly. So it's kind of the same thing when you look at the house as a system, right? You look at your mechanical system, you look at your ventilation system, you know, what's more important, the furnace, AFUE value, or the HRV, the percentage of heat loss? You know, so those are two things to look at. And you compare those to windows, we have all these different things on the window label. So now if we go through these one by one, the U factor, which window's best? Here's an example of one where it lists the metric and the imperial value. Right, 1.19, there's your winner right there for U value. However, that only would worry me on the north side of a house in a cold climate. If I take the next number and I look at this number, which number's the best? Well, I want to look at the size of the window, the area it's covering, and what's the ability for heat to dissipate in that house before I look at anything. And then I would look at the overall U value, or the solar heat gain value. Because if I'm looking at these numbers here, 27 to me is too low for a small amount of glass. 27 might be too high if I have massive amounts of glass, right? So we have to look at that and look at all the different details. If I'm looking at the visible transmittance, this one's getting pretty dark compared to a 53. But really only if you're comparing it side by side. So those are factors that you want to take into consideration. And then the energy rating, if you were putting this window in a cold climate, this is not going to perform very good at all. That's a terrible window in a cold climate. So those are the factors. Go ahead, Mark, just jump in.
So let's say you've got a project, you're trying to make a decision about what windows you're going to ask your supplier about, and you want to know what solar heat gain coefficient am I looking for the type and size of windows that I'm considering for my house. Who do you ask? If you don't memorize that answer from this presentation, if you're not, an encyclopedia of window knowledge after these 4 hours, who do you ask about what windows should I be considering for my house? How many of you work with an energy advisor on your projects right now? I would suggest to you that that is the right place to start. If you're working with an energy advisor, they're energy modeling your homes or they're helping guide you through code compliance, they're going to have some feedback for you on that. They're an excellent resource to help you understand that balance of free energy from the sun that helps your compliance versus homeowner comfort issues that you might be risking depending on the design of your homes. If you didn't put your hand up and you're not working with an energy advisor yet, then start looking, because I think they're going to become much more important in the process as the codes continue to go this way.
Yeah.
It's a bit of a shameless plug. I am an energy advisor, but I don't work in Alberta. So you're going to have to talk to your local energy advisors and find one that knows your product and knows your climate and knows your building style and methodologies as well, so they can be a useful resource for you.
Yeah, exactly. So just go talk to Chelsea.
I have 2 questions here. We were talking about CR before.
Yep.
How do we test CR rating? I mean, how do you know, how does it perform in terms of condensation? The second one is the condensation number. I don't see it here. It seems like these are mandatory, but CR is volunteer. It's been driven by bylaws, or is it volunteer?
There's no requirement for CR, for condensation resistance, and it's a theoretical value. So it's a calculated value based on what they anticipate is going to be the reflection of the heat and how much absorption of the heat is going in there. So it's fairly accurate, but it is this a theoretical number.
It's not mandatory code, it's not driven by code.
No. Yeah, these are the mandatory numbers that you're going to see in Canada under NFRC, National Fenestration. So you'll see these numbers on your energy or on your window schedule. So there's the values there. So this is a ER30 window, so it's a pretty good window, 0.91 with a solar heat gain of 0.18. So you put this in the house, and it's the only window in that room, how much heat gain are you going to have? Nothing. You're getting no free heat from the sun. So if this is one of 30 windows in that room, this is the appropriate value. If this is the only window in that room, that might be way too low. And you're spending a lot of money, and it's going to actually hurt you in the long run. How about these windows? You look at 0.23, 0.32, right? The U values are what? Does that look like a reasonable U value? Or does that look like a ridiculously energy efficient window?
It's like imperial.
That's like R12. That's like R20, right? But it's an imperial value. So if I want to get that, I just multiply by 5.678. And then I can get my imperial value. Because this happened, I don't know about in Ontario, but here, we get this all the time.
It happens all the time.
And every time it happens, somebody thinks they found the best deal going in Windows. And they're not going to tell anybody about it. They're going to get that supplier all to themselves. But yeah, it happens all the time.
Yeah, exactly. And then the solar heat gain is pretty normal value, right? 0.32, 0.27, pretty average for an average house. And here's where it comes into the different window percentages, because this is what dictates both your free heat from the sun and your peak cooling load. Does everybody understand peak cooling load? So peak cooling load, when you do an energy model and you put the window values in, and you put the positioning of the house, and you put the environment that the house is going in, it's going to tell you how much sunlight is coming in through how much glass, through how much solar heat gain, and what's the risk of overheating that house based on a comparison to a reference model. And there's a little line about 3/4 of the way down through on your 2000 report that'll say peak cooling load. And you'll either have it in watts per meter squared or you'll have it in BTUs. And you compare that to the reference house. And what it's telling you is when you're overheating that building. So it's a very valuable number. And your energy advisor can go through that with you. But if you're doing the work, if you're receiving the data from the energy advisor, you can just look down there and compare reference to proposed house, and you can see if you're overheating it. And generally where that's going to happen is when you exceed that 22% that the building code talks about. right? If you're into the less than 17%, it's not unreasonable to look at high solar heat gain windows. Like when I'm doing energy models, I'm probably looking at a 0.35 to a 0.4 that I would recommend to a builder, just because, you know, some builders are down at 7% in FDWR. And if you're down at 7%, there's no reason you can't go to a 0.45. I think 0.65 is a little high, but these are the averages, and it depends on the windows and where the windows are located. You get into the average between 17 and 22, you're looking at a solar heat gain of 0.45 to 0.3. You get into custom homes where you're up in 30, 40% glass. Now you got to get down to the 0.3 or more. So you're just looking at the overall average, how much glass is in the house, and specifically how much is south facing. Give you an example. We do an energy model, or I used to do an energy model of this one particular model a builder had. It was designed to sit on a corner lot. And when it sat on the corner lot, on this corner, there was so much window there that it was 25% better than code. And then when they put it on the opposite side of the street, it was in the shade, it was 10% below code. Just from the windows, solar heat gain. So how do you balance that out? Well, if you start to reduce your solar heat gain values, you can get a little more, you know, it's not as much influenced on the positioning of the windows or the percentage of the windows. Mark, you have a comment.
Yeah, we're going to dive into that in the next one, but I just want to mention these slides now. They mentioned that solar heat gain coefficient is not in the code, but it is going to be.
Yep.
The 2025 National Building Code has now been recommended to include solar heat gain coefficient with a maximum allowable solar heat gain coefficient based on the percentage of window to wall ratio in your home when you're using prescriptive. That's a lot of detail. The takeaway is it's coming into codes, and that's why we're presenting it in context like this.
Yeah, exactly. And I know when we did the first code, we could cheat the system. We could run everything at, you know, 0.65 and they performed beautifully, but we were overheating those houses ridiculously. So now we've got the peak cooling loads that have come in, and in the next code cycle, we'll go even further. So the path to windows, if we're looking at the different windows, here's all of the things that we need to consider, right? We've talked about the IGU, the coatings, the gas. We talked about the amount of glazing, the frame, the spacer. All of those things impact the performance of the window. When you look at the right and you look at the range that you want to achieve, the window design elements that are needed go up extensively. So if you're into the 1.05 to 0.95, a triple glazed window with no coatings typically will meet that need. You might need one low E coating. But once you get into this really high performance window, 0.82 to 0.65, you need every one of these things to be met. So it becomes more and more and more critical. Anybody using windows that are lower than 0.82? No? Okay. What's the lowest window you've worked with in Canada? Mark?
I've been involved in a few passive house projects that will find windows down in the 0.8, 0.78, I think is maybe about the best I've seen. They've been very difficult to source historically because this hasn't been driven by codes yet. So it's certainly aspirational still, I think, for many manufacturers. But the window manufacturing industry at large is very much up to speed on what this direction is and where the demand is going to come from. And even the manufacturers that are supplying the builders that are doing thousands of homes a year are looking at how do we move towards these lower values and make them cost effective as they do that, understanding we're going to have to get there at some point, for sure.
Yeah, exactly.
Question for you. You just said you have come across a window which was 0.8. Was that a venting window or a fixed window?
It was, and I'm going to be careful how I say this, it was an imported European style tilt and turn. And the reason I'm cautious saying that is that windows coming from overseas are tested using different test standards, and you cannot compare directly a European test standard U value to a North American test standard U value because they test them at different temperatures and different sizes. But we did get values for both in this case, and so the 0.78 I gave was by the North American standard for that window, but it was a tilt and turn window.
Yeah. Yeah. There's some fantastic windows. I know a couple of builders that are bringing windows out of Poland, and they're getting very, very low U values. But again, it's because the European standard kind of artificially changes compared to the North American standard. But yeah, those are things to be aware of. All right, just to finish off on a few little points here, have you heard of electrochromatic glazing? You've probably seen the Lux commercial on TV. So you're familiar with, if you've seen that commercial, you're familiar with electrochromatic glazing. Vacuum glazing, did you know that IGUs are not vacuum? Right? When you have an IGU, it's a sealed unit, but it's not vacuum sealed. This is revolutionary to me because, you know, I've been doing this for a long time, and about 8 or 10 years ago, I realized these are not vacuum sealed. I always thought they were. And then it talks about thin triples versus lightweight triples. So these are new technologies. So electromagnetic or electrochromatic, basically what it is, you put a small charge through it, and it turns translucent. You can't see through it. So if you've seen that commercial on TV, somebody goes over to the window, you can see right through it, they push a button, it sends a small charge through, and it turns opaque. Pretty cool. So the technology there is available now. They're looking at that for, you know, low E coatings and different coatings that they can put on, you know, to try and reduce the heat gain at certain times of the year. Interesting technology. Very expensive technology. The other new technologies is vacuum glazing, where you suck the air out of the glazing. The problem with it is on large pieces of glass, it'll suck the two pieces of glass together. So how do you keep that from happening? So this is a new process they're working on. There's some windows out there, you know, smaller units that are available that you can get vacuum glazing on. What would the benefit of vacuum glazing be? It's the density, it's the air in between. So the less air in between, the less convection you have, and the higher the U value of the window goes. So there is some benefit to that type of material. And then new technology, thin triples. So they talk about thin triples or lightweight triples. Really the difference between the two, it comes down to the frame itself. Like you can make an overall triple glazed window that's relatively lightweight. You make a smaller frame, you put smaller glass panels in, things like that. And then there's the thin triples, which is these tiny little thin panes that we talked about earlier, right, that are in between. Now, those I think are a long way off becoming a standard product, but thin triples are fairly common. Thin triples also use krypton gas, which is very expensive. So that's what makes those windows a super expensive product. So those are some options. So the takeaway, when you get a window schedule and you look at that window schedule, is this what you want in that house? Right, so you've ordered the windows, they're not on site. Here's the window schedule, double check it to what you ordered. What's missing on here that you may have to ask about? Sorry? Yeah? Yeah, condensation resistance.
Energy rating.
Yeah, you might need an energy rating depending on if you're putting it into a software or not. So those are things now you understand. You might not know where the coatings are on the glass, which would dictate condensation resistance, right? Is the coating on the inside surface? What's the durability of that? If the painter comes along and cleans the windows before the homeowner moves in, use a razor blade, is he going to take that coating off? Right, so those are things to think about when it comes to the windows. The takeaway here, what's the label tell you? This is what you got in the house. This is not what you ordered necessarily. This is what you got in the house. So the label's pretty important. Does your framer understand that? If you order different windows for the north and the south side, did he check the label and make sure that it was in the right location? So the label's pretty important. The solar heat gain is important when it comes to the percentage of glass that you're putting in. The more glass, the lower the solar heat gain, the lower the heat is going to build up in that building, which reduces the risk of having too high a peak cooling load. All right. So that takes us through our first section. I'm going to turn it over to Mark.
Thank you. We'll just have time for a couple of questions, and then I'm going to flip the agenda a little bit since the coffee is here and we didn't get a chance to have it before. So any questions for Darrell on the first presentation before we dive into coffee? That's a leading question, but
I should be there. If you go back to your second last slide where you were showing the labels,
Yes.
I mean, we are window manufacturers, so I just want to take this opportunity to educate
Excellent.
the people you know. If you look at the first label, it says it has an NFRZ, which is in our case, it will be NRCan. That is most likely because it's an Energy Star window, you see that label. These windows here, 1.44, 2.2, they are not Energy Star. 1.1 is Energy Star, but I don't see that Energy Star label. So what does it mean is anything under 1.2, if it has that label, it means it's Energy Star. Otherwise, rest of the windows except the 2.22, those meet building code, which is 1.66.
Yeah, exactly. And if we're doing, as an energy modeler, if we do a renovation or a retrofit and somebody puts Energy Star windows in, not only do they have to have a label like this, they have to have the Energy Star logo on the label to indicate that. So, yeah, we haven't got into Energy Star in this presentation, but that's excellent information to know.
Yeah, thank you for that.
Thank you.
And I will point out as well, actually, we pick on this window. It actually happens to be a skylight in this case. So there are going to be very different numbers associated with skylights because of their interaction with the sun at that level. That's why we included that weird looking one in there.
Yeah.
Any other questions on this first part of the presentation? Very technically dense. Joe, go ahead. Running this back to you.
So one of the things that's coming up in wildfire resistance standards is a requirement or a request for a tempered glass pane as in your triple plane unit. So how does that affect, or does it affect any of the technologies that you introduced today in terms of trying to improve energy performance?
Excellent question. From many resilience perspectives, including hail, but really with regards to wildfire, the requirements for wildfire resilience are now asking window manufacturers, window purchasers to consider tempered glass for the exterior pane, ideally, and frame material that's not vinyl. And vinyl is by far and away the most common window material in our industry, but it just doesn't hold up to heat when you're exposed to wildfire. So unfortunately, the recommendation at the moment is a metal protected wood frame window with a tempered exterior glass layer. You can achieve all of these performance values with that window. Tempered glass itself doesn't really play into this as much as the coatings and the number of panes of glass do. But as you can expect, the window that I just described is probably the most expensive one that you've considered. And that's a real challenge. So it does come down to, we always talk in our industry about good, better, best. We want to always at least do a good job and look for opportunities to do better and certain scenarios where we want to do the best. If you're building in a very high wildfire risk environment, then the cost trade-offs may be worthwhile in that scenario. And to answer your question directly, it won't negatively impact these numbers in a significant way. But it will be uncommon. Because where do we usually see tempered glass in these assemblies? We usually see it on the inside pane for protection against breakage from the interior. But the reason wildfire wants it on the exterior is because that's where the heat stress is coming from an exterior wildfire. Everything is sort of flipped. So it's another whole day to explore wildfire resiliency questions and hail and wind, which are all risks across Alberta. But as it comes to windows, it's another exploration point for us collectively to learn more about. It's a great question.